right, for anybody who's watching this later, hi, we'll get started in a minute. I am just uploading the share link so people can get on, and we'll get started in about 3 or 4 minutes. Again, if you just popped on, we're going to get started in about 1 minute. So just hang out for a second. We will be back in action in a minute. Okay, so let's get started, and if people hop on in the meantime, that's great, but we are going to be talking optimization and related rates here. So one of the things I want to remind you guys is that all of the live streams from last year are still up. So it seems like I'm kind of going through random topics with these live streams. I'm just trying to fill in the gaps of what I didn't already make a video about last year. So if you're wondering, where is this topic, feel free to just send me a message. But we are going to talk optimization and related rates because that's definitely something that comes up. Now, one of the things I will tell you with optimization is typically this is not a big topic on the AP exam. And AP teachers, we don't love that. We think it's an important topic. It's like one of the biggest reasons you would take a calculus class is to be able to find the best or the worst of something. But for the AP exam, it's just not a major focus. So if you've noticed we haven't spent a lot of time on that, there's a reason why. The other thing I would say is, if you're going to see it, it's probably going to be one question and probably in a multiple choice. And what you need to remember at the end of the day is that these are just problems where you're trying to find a max or a min. That's all they are. So we're going to do one or two of these, but we're not going to spend a ton of time on them because right now we're talking maybe one and maybe multiple choice. So it's not going to be a huge deal, but we'll go through the calculus because it's good review on curve sketching anyway. So remember with optimization, your key here is that you want to figure out what you're trying to optimize. And when you see optimize, you should be thinking max or min. And then also think about what your constraints are. And constraints are like your limiting factors, right? We need to be able to put those into equations. So let's start with a simple one, and then we'll get into one where we have a little bit more interesting algebra because we're really starting with our, simplest case here. So find two positive numbers such that their product is 192 and the sum of the first plus 3 times the second is at a minimum. Now, when I see that word, that's how I know that this is something that I'm trying to optimize because I know I want to find a min. And remember, a min, we're talking about that on a graph, and I'm talking about my sign chart going from negative to positive. So really, that's what I'm looking for. Now, let's find two positive numbers. So let's call those x and y. And again, we could write let statements here, but this is just a quick review. Their product is 192, and the sum of the first plus 3 times the second is at a minimum. So here's what I'm trying to optimize. The first plus 3 times the second, and that's what I'm trying to optimize. So you can call that O, you can call it whatever, but that's the equation that I'm trying to optimize. So I'm going to call that O so I remember that. Now, what's the constraint? Well, I know that their product is 192. So that's the constraint that I have to work with. I know that this is the situation I want to actually find a max or min on, but this is the constraint that will let me get it in terms of one variable. So now from here, this is just a system of equations. So I'm going to isolate one of the variables in here. Let's say I isolate x. So that would be 192 over y. And I'm going to plug that in. So this would be 192 over y plus 3y equals, and I guess O is a confusing letter to use there because it looks like a 0. So let's maybe make that a Q, whatever you want to make it. Now, from here, what I'm saying to you is, this is my function in terms of one variable. Can you find me the minimum, right? And so now this is just a min-max problem. So this is really 192y to the negative first. So I'm just going to rewrite that. So my derivative would be negative 192y to the negative second plus 3 equals 0 because the derivative of that side will be 0, right? And I want to find the min or max of that. So this would be negative 192 over y squared equals negative 3. And we can make that a proportion and cross multiply. So negative 192 equals negative 3y squared. So y would equal the square root of 192 over 3. Now, something to remember here is we also need to look for where this is undefined. So this derivative does not exist at y equals 0, which means that is one of my critical values, right? Y equals 0. And then 192 over 3 is 64. So that means y would equal plus or minus square root of 64, which is 8. Now we should have a plus or minus there too. So I've got 3 critical values. I've got 0, negative 8, and positive 8. Those are my critical values. And we could test all of them to see which one's a minimum. But notice our other constraint was that they had to be positive numbers. So that means that 8 should be my solution. Now, if we check that, if we plug that in here, right, and we plug in 8, and I notice this goes from negative to positive, that means it is a minimum. And so what we have there is that the first number is 8. And so then the second number would be 192 divided by 8, or you could plug it into the other equation, and that would be 24. So there are my 2 numbers. So remember, an optimization problem is really just a min-max problem where you need to find your critical values and then check that you actually change signs. Okay, so combined perimeter of a circle and a square is 16. Find the dimensions of the circle and the square that produce the minimum area. So looking at this, I see that word minimum there. That's what I'm trying to minimize is my area. So area, we're talking about a circle, so pi r squared. and a square, which is s squared. So that right there is what I'm trying to minimize. And what is our constraint? The perimeter is 16. So that's 2 pi r plus 4s equals 16. So this is my constraint, and the other one is what I'm trying to optimize. Now we're going to isolate one of these variables. It doesn't matter which one you choose. I'm going to choose to solve for s, let's say. So that would be s equals 16 minus 2 pi r all over 4. And so plugging that in, I'm getting pi r squared plus 16 minus 2 pi r, or 4 minus pi over 2 r squared. So there's what I'm trying to optimize. Now, to actually optimize this, we need to take a derivative of it. So you can do that using either multiplying this out, right? So you could use product rule, or I'm just going to use chain rule on it. So I want to set that derivative equal to 0. So this would be 2 pi r plus, now this will be 2 times 4 minus pi over 2r times the derivative of the inside, which is negative pi over 2. So there's my derivative. And let's do some solving here. So 0 equals 2 pi r plus, let's see, those 2's will cancel, negative 4 pi plus pi squared over 2r. So solving for r, you've got an r in this expression and this expression, or those terms, sorry. And so I'm going to move the 4 pi over and factor out the r. So that would be 2 pi plus pi squared over 2. And then you can divide that over to get your r value. Now it says find the dimensions of the circle, so you've got your radius, and once you have that, you can go ahead and plug that back in to get the dimensions of the square. So again, another example, and really what I want you to focus on is getting it into this form, which is where you'd have just one variable, right? Not a major topic, but let's try a couple more quick little ones. So find the point on the curve, y equals radical x, closest to 4, 0. So what I'm really looking at here is that I have the point 4, 0, and I have the point x, y, or x, radical x. And what I'm trying to do is minimize the distance, right? I'm trying to minimize the distance there. So I would use distance formula. So square root of 4 minus x squared plus 0 minus radical x squared. There's my distance formula. And we can simplify that a little bit. So this would be the square root of 4 minus 8x plus x squared. I'm sorry, this would be 16 minus 8x. And then plus x. So really here I've got that this is x squared minus 7x plus 16. Now let's take a derivative of that. So d prime would be 1 over 2 radical that times the derivative of the inside, which is 2x minus 7. And what we're looking at here is this quadratic, which has no real solutions. You could try, but it doesn't have any. And then 2x minus 7. So this will never be undefined over the real numbers. So I'm just going to set 2x minus 7 equal to 0. And so x equals 7 over 2. Now, it's point. So first of all, you'd want to check that that's really a minimum, that it goes from negative to positive on the derivative. But then we would look for the actual coordinate point. So this point would be 7 over 2, and then the y value would be the square root of that. Okay, last one. A rectangle is bounded by the x and y axes, and the graph of this is shown. One of the length and width would give us maximum area. So area here is just going to be x times y, because this is our x value, and that is our y value, right? And my constraint is this, that we've got x times 6 minus 3/4 x. And so now I've got it in terms of one variable, and I can keep going from there. So area equals 6x minus 3/4 x squared. And let's take a derivative of that. So a prime is 6 minus 6 over 4x. And set that equal to 0. So 0 equals 6 minus 3 over 2x. And then we could keep going and solve from there. So again, same idea is that you want to solve this. So multiply by 2/3. and then actually a maximum, so make sure you go from positive to negative. And to find your y value, plug it back in. So 6 minus 3 times, or 3/4 times 4, which would be 3. So the length and width should be 4 by 3. Okay, so I'm going to move on from optimization there. Again, this is not a major topic. This is not something that I want you spending hours and hours studying. Glance over it, and it should be a multiple choice where you can kind of reason through it and come up with an equation. But related rates is what I'm going to spend a little bit more time on. So remember, with related rates, we're talking about things that vary with respect to time. And so we want to look at how they change with respect to time. So that means we're going to be doing implicit differentiation, and we're always putting a d whatever dt after. So let's start with a sort of simpler one. So the radius of a circle is changing at a rate of 1/pi inches per second. At what rate in square inches per second is the area changing? So let's see what we have. Radius of a circle is changing at this rate. So dr dt, I'm going to say r is radius, is 1/pi inches per second. It doesn't tell me whether that's increasing or decreasing, but since it's positive, I'm going to assume that this is increasing, okay? So that's something important to know. At what rate is the circle's area changing? So I want dA dt when r is 5. And this only happens at a particular moment in time, so we're going to have to be careful with when we sub that in, right? So what I'm going to look at here is, okay, I need a formula that will relate r and a together. So I know the area of a circle is pi r squared. So let's use that. Remember that I cannot sub in the 5 yet, because that is a quantity that changes. So I'm just going to take a derivative with respect to time. So dA dt equals now 2 pi r times dr dt. And I know that r is 5. They told me that. And dr dt is 1/pi. So 2 times pi times 5 times 1/pi. So your pi's wind up canceling. And so this is just 10. And if this was a free response, you'd include square inches per second there. All right, let's look at another one. Let's get a little harder. So in the figure above, a hot air balloon is rising straight up from the ground and is tracked by a television camera 300 feet from liftoff point. And luckily, they labeled that for us. At the moment when the elevation is pi/6, so this is not always true, right? This is at a point in time. The balloon is rising at a rate of 80 feet per minute. And rising would be the rate that this changes. So here's what I know. I know dy dt is 80 at the time when theta is pi/6. And remember when we did this, we'd sort of organize it by what's always true versus what's true at a point in time. That's what I'm doing in my mind here. So at what rate is the angle of elevation changing? So what is d theta dt at that moment? That's my question here. So let's think through this. We need some information here. So we need some kind of equation that's going to relate theta and y together, because I know that those are related here. So when I think about that, especially because I know this 300, I'm thinking tangent. So tangent theta is y over 300, because it's opposite over adjacent. That 300 never changes, so I can leave it that way. So taking a derivative of this, I would have secant squared theta times d theta dt equals 1/300 dy dt. You could also use quotient rule there, but remember that y is just, y over 300 is 1/300 times y, right? So that's all I did there. So let's think about what we know. Secant squared theta, well, I know theta is pi/6, so this is secant squared pi/6. D theta dt, which is what we want, equals 1/300 dy dt, which is 80. So that's what I'm solving there. So let's think about secant squared theta. That is cos of pi/6, and then it's going to be the reciprocal of that. So cos of pi/6 is radical 3/2, which means secant of pi/6 is 2/radical 3. So if I square that, I'm actually going to get 4/3 d theta dt equals, this will be 8/30. We could keep going. We could make that, let's see, those are both divisible by 2, so 4/15. And then if I multiply this through, I'm going to multiply by 3/4. And so I wind up with 3 or 1/5, and that is 0.2. And remember, that's something you should be able to do without a calculator, right? Getting to that point without a calculator. Okay, let's look at the next one. So remember, you guys can be sending questions at any point here. So radius of a sphere is increasing. Let me actually shrink all this stuff down up here. Oops. So rate is at a constant rate. So whatever dr dt is, we know it's constant, right? And at the time when the surface area and the radius of the sphere are increasing at the same numerical rate, what is the radius of the sphere? So ds dt equals dr dt. That's what we're saying here, okay? So at that point, when that's true, when would this happen? Now, dr dt, we don't know, but we know it's constant, right? And the surface area is S, so 4 pi r squared equals S. So ds dt would be 8 pi r dr dt. So here's what I know here. I know that ds dt, which is this, equals dr dt. So I'm going to set those equal. So 8 pi r dr dt has to equal dr dt, right? Which means, and there's a bunch of different ways you could do this. You could subtract this over and go from there. But this really means that 8 pi r has to equal 1, right? Because they're multiplying by the same thing to get dr dt. So if I have that, then I have r is 1 over 8 pi. Now, you could also move everything to one side here, factor out a dr dt, and you'd get to the same answer. Okay, let's look at another one where you have to do some thinking through your variables. So looking at this next one, the volume of a cube is increasing at a rate of 12 inches cubed per minute. So dv dt is 12, and it's positive because it's going up. How fast is the surface area increasing when the edge is 20? So when S, let's say E for edge, is 20. Okay, so let's start with what we know. Volume of a cube is increasing at this rate. So volume equals the edge length cubed, and surface area is 6 times the edge length squared. So those are the two things that I know. So in order to figure out ds dt, we need dE dt, right? So ds dt would be 12 e dE dt. Whoops. Scroll back down. Okay, now for volume, right, we can figure that out. So ds dt is what I want. I know E, so I just need dE dt. But volume's going to let me figure that out. So let's use volume. dV dt equals 3e squared dE dt. So I'm going to use this formula to figure out that. So I know dV dt is 12. I know this is 3. And E is 20 dE dt. So this would be 3 times 400, which is 1200. And so we have that dE dt should equal 1 over 100, or 0.01. So dE dt is 1 over 100. Okay, 12 over 1200. So let's plug that in now. ds dt equals 12 times 20 times 1 over 100. Notice it's a pretty easy number to divide by. So this is going to be 240 over 100, which is 2.4. Now, which one of those is this answer? That would be letter D, because that is 2 and then 2/5. Okay, let's look at this next one. That's another kind of like weird variable one. We're going to do a funnel, everybody's favorite. Oh, this next one. The radius of a circle is decreasing at a constant rate, and they give you that rate is 0.1 centimeters per second. So let's start with what we know here. We know that dr dt is negative 0.1. In terms of circumference, and so that should make you think, okay, circumference is 2 pi r. So let's keep that in mind. What is the rate of change of area of the circle in square centimeters per second? So let's start with what we know. A equals pi r squared, right? So dA dt would be 2 pi r dr dt. And so notice, like, I'm not even addressing this whole in terms of circumference thing. I just know they want me to find dA dt, so I found an equation for dA dt, right? So now what I would say is, okay, well, how can we use what we know to help us? So dr dt is negative 0.1. And they want this in terms of circumference. Well, circumference is 2 pi r. So that's actually circumference right there. And so this is just b. So that's really a matter of just substituting into your equation. Okay, last one that we're going to do, let's talk funnels. So remember when we talk about these kind of shapes, and not just funnels, but cones more likely. Funnels don't have to be cones, but this one tells you it is. So a funnel in the shape of an inverted cone is 30 centimeters deep. So we've got this cone. We know that the depth here is 30. And a diameter across the top is 20, so I know my radius is 10. And I use radius there because I know radius is the thing that's in all the equations, so it just makes more sense to me for me to just label that. Now, liquid is flowing at a rate of this. Now, notice that's in centimeters cubed per second, so that's dV dt. And since the volume is getting smaller, this would be negative. At what rate is the height decreasing? dH dt. At the instant when the liquid in the funnel is 20 centimeters deep, when H equals 20. So notice they're giving me V dV dt. They're asking me for everything to do with H. There's nothing to do with radius here. But remember that, like, as this water level gets lower down, the radius will change, right? So what we need to do here is remember that there's a possibility that you might have similar triangles where that's 10 and that's 30. And whatever that is, that's R and that's H. And so we have this relationship that R over H is 10 over 30. And I know that I want this all to be in terms of H. So I'm going to solve this for R. So R equals 1/3 H. This relationship will always be true. So I know that the volume of a cone, and they would give you this, is 1/3 pi r squared H. So before I do any calculus, I'm going to get this all in terms of H at least. And so now when I actually take some derivatives here, this is all going to be in terms of one variable. So I've done that here, right? There's my go around at that. And so I'm going to just simplify before I take a derivative. So this would be 1/27 pi h cubed. Remember to square each of those. So this dV dt, which we know is negative 12, is 1/27 pi times 3h squared dH dt. And now we're just plugging in. So this is negative 12. This is, let's see, pi over 9 times 20 squared times dH dt. And I want dH dt, so let's just solve this. So negative 12 equals 400 pi over 9 dH dt, and dH dt would be negative 12 divided by 400 pi over 9. Remember, in a multiple or in a free response, you could leave it like that, but you could also say, okay, this would be negative 12 times 9 over 400 pi, and you could keep going from there, but you don't need to do that. The one thing that you should have, though, are units. So your units here, because we're talking about the change in height, which is measured in centimeters, should be centimeters per, let's see, second. And I would say don't simplify. Leaving it right here is totally fine. Okay, so guys, that was a little mini crash course on optimization and related rates. I would tell you to remember is that there are full live stream reviews on all of this stuff, every single topic back in that unit. So if there's something you have questions about, go to the live streams from that unit and check on it. But this is just a quick little crash course to get you updated. So next live stream is Tuesday night. Your final starts Tuesday or Wednesday, depending on whether you're in mine or Mrs. Belton's class and you have A or B day. And good luck. I hope you guys had a great break. And